Here we introduce covariance matrices and consider some of their properties. Consider a random vector x consisting of n random variables arranged into a column vector. This t here denotes the transpose of the row vector. Furthermore, let mu I denote the mean of the ith random variable, and let mu x denote the column vectors of the means of the random variables x1 up to xn. The covariance matrix sigma x of the random vector x is then the matrix whose ijth element is the covariance of xi with xj, as shown here. Notice that this is precisely the expectation of the column vector consisting of the random vector x minus its mean vector times its transpose. The first vector here is an n by 1 vector. The second vector is its transpose and is therefore a 1 by n vector, and hence their product is an n by n matrix. Now for some definitions from matrix theory, suppose we have a square matrix, an n by n matrix A. We say that A is symmetric if A is equal to its own transpose. In other words, if the ij element is the same as a ji element. Basically, this just means that A is symmetric about its main diagonal. A is said to be non-negative definite or positive semi-definite if it is the case that x transpose times A times x is greater or equal to 0 for any n-dimensional column vector x. It is positive definite if x transpose times A times x is strictly greater than 0 whenever x is a non-zero n-dimensional column vector. Note that x transpose times A times x will be a 1 by n times an n by n times an n by 1. In other words, it will be 1 by 1 and therefore will be just a number. Here's a simple proposition. Suppose that we have an n-dimensional random vector x whose covariance matrix is sigma x. Suppose further that A is an m by n matrix and that y is equal to A times x. In other words, y will be an m-dimensional random vector. In that case, the covariance matrix of y is given as follows. It's the product of A times the covariance matrix of x times A transpose. To prove this, first note that the mean vector of y is easily seen to be A times the mean vector of x. By definition, the covariance matrix of y is the expectation of y minus its mean times that transpose of y minus its mean. Since y is equal to A times x and the mean of y is A times the mean of x, we obtain the following expression. Now recall that taking transposes reverses the order of multiplication. In other words, A times x transpose is just x transpose times A transpose. And this means that this expression here simplifies to the following, where now we've taken out the constant matrix A and A transpose. What remains in the middle is precisely, by definition, the covariance matrix of x. As a result, we have the following proposition. Covariance matrices are both symmetric and non-negative definite. To see this, suppose that sigma x is the covariance matrix of an n by 1 random vector x. It's obvious that the covariance matrix is symmetric because the covariance operator is symmetric. The covariance of x with y is the same as the covariance of y with x. Now suppose that A is an n-dimensional column vector and let y be the random variable which is A transpose times x. This expression here will be a 1 by 1 matrix, in other words just a number, and can be expressed as follows. Then by the previous proposition, the variance of y, which is just the covariance of y with itself, is A transpose times the covariance matrix of x with A. Since the variance of y is non-negative, it is the case that this expression here is non-negative. And since this is true for any vector a in R to the n, we see that sigma x is non-negative definite. Finally, we consider Cholesky decompositions of symmetric non-negative definite matrices. It is easy to show, and left as an exercise, that any matrix of the form A is equal to B times B transpose is symmetric non-negative definite for any matrix B. Conversely, the next theorem states that any symmetric non-negative definite matrix A can be written in the form B times B transpose, and moreover B can be taken to be a lower triangular matrix. Here is the theorem. A real symmetric matrix A is non-negative definite if and only if there is a lower triangular matrix L such that A is equal to L times L transpose. Here L and L transpose form the Cholesky decomposition of the matrix A. Notice that this is an if and only if. In particular, any covariance or correlation matrix has a Cholesky decomposition. And as we shall see, this fact is very important for the simulation of correlated random variates. Now, most scientific programming languages will have an efficient built-in implementation of the Cholesky decomposition. This provides an easy way to test if a matrix is symmetric positive definite. If the Cholesky algorithm succeeds, the matrix is symmetric positive definite, and if it doesn't succeed, then it isn't.